Hey, thanks for watching. This is another video that was filmed live at the HVACR Training Symposium in Claremont, Florida. This is my friend Jim Bergmann talking about combustion analysis, specifically using the BluFlame Combustion Analyzer from AccuTools, which is a really great tool that connects with some excellent diagnostic software that Jim helped to develop. So hope you enjoy this. The quality isn't perfect, but we tried to edit it as best we could. Jim was kind enough to share the slides. Really great training. If you want to find out more about the BluFlame Analyzer, you can go to the AccuTools website, or you can also find out more about everything Jim's doing over at measureQuick.com. Hope you enjoy the video.
You want to be outside, right? Calibrate your analyzer outdoors. Make sure that you're getting fresh air in that analyzer, and then walk through the home with that analyzer about chest height. CO does not stratify. It does not go up to the top or does not go down to the bottom. It mixes very evenly with the air in the home. So about chest level, walk through all the areas of the home. Make sure that you don't have CO on there. A couple of characteristics of carbon monoxide. Odorless, colorless, tasteless, mixes well, right? It does follow the air in a structure, okay? Now, and it is poisonous. A lot of people think you can put, like a lot of these personal CO meters and things, like right in the hot air stream of the furnace. Many of them are not temperature compensated, and they will show CO that does not exist, especially on some of the old ones. Some of the newer stuff's a little bit better, but you got to make sure that you're using the right tool on that. When you get CO symptoms, and this is what happened to the lady that Bill and I went out there. The lady started getting CO poisoning. She thought she had the flu. She stayed home. So she's in this home with high levels of CO. She's got headaches. She's got dizziness, nausea. She's got the flu symptoms. She's tired. And here, her home is killing her, right? And I think Joe will tell you later on, he's going to be doing a presentation on healthy homes on there, that your home is something that we don't think about all the time. And you guys, when you walk into areas, you know, you should kind of be aware of what you're walking into. Years ago, I remember when I was probably about 19 years old, I walked into a flower cooler and had a dirty evaporator coil. So I go in with my tank of CO2, I'm going to blow that out, and I walk into this little, maybe 8 by 10 cooler, and I start blowing it out with CO2, and all of a sudden I'm starting to get really dizzy. I'm thinking, what the heck's going on here? And I realize I'm displacing all the oxygen in the room, right? Those are simple mistakes. It's the same thing here. You walk into a big boiler room, and we've seen some pretty big stuff dumping CO in spaces where, you come back after lunch, and you think the Chinese got you, and again, you're exposing yourself to CO. There's some CO health effects. It's all in the book there, but 9 to 13 parts per million is a typical 8-hour exposure limit we want to see, but you can get an idea when these levels get higher, they can cause death in a matter of minutes. CO displaces the oxygen in your blood, okay? Your body can't tell whether you're getting carbon monoxide or you're getting oxygen. It just displaces it. So as you're breathing, what's happening is you're breathing into CO, it's displacing the oxygen, you're getting no air to your lungs, and your body, you actually die from basically from lack of oxygen to your brain, right? That's what causes death. Don't get fixated on the appliance. Make sure that when you're testing, a lot of guys, when you go out there and somebody has CO in their home, again, they try and fix everything at the furnace. Look at the hot water tank. Look at the stove. Look at the oven or range. Look at auto emissions is probably the biggest one that we see. People backing their cars into the garage. Automatic car starts. We had an incident in Ohio where somebody was killed. Their son bought them a automatic car starter for Christmas. They wired it up to the car. The guy sat down in his recliner. It hit the button, started the car. Car was in the garage running, and it killed the occupants of the home. So these type of things do happen in there. Fuel burning space heaters, fuel burning boilers, all these things can cause CO. Draft and spillage testing. You want to make sure, a lot of guys when they're doing their combustion testing, we'll walk through all the process, but one of the things when you're making your draft test in there, you need to be away from the draft diverter. 12 to 18 inches above the stack here when you're doing draft testing. A lot of guys want to do all their testing down here, and I'll talk a little bit about the draft diverter later here, but we want to make sure that we're testing in the flue. Draft testing is one of the first things we do when we're doing combustion analysis. We want to make sure that we're going to ventilate those products up the stack. So a lot of times before I go in, what I'll do is punch a hole in there, make sure I have some draft, make sure things are going to go up the stack. Sometimes you won't have draft, especially if the chimney's cold, but it's important to realize what you're walking into when you do this type of work. So you want to make sure that we're going to make sure we have some draft. So let's talk about the function of the draft hood is. The draft hood actually separates the appliance from the draft. So if you look here, I've got this broken in two right here. And the draft hood, the reason they invented the draft hood was fires, okay? If you have properly burning appliance, all you're going to get is carbon dioxide, water vapor, and heat. Right, this carbon dioxide it's a pollutant, but it's not gonna kill you. You guys burn your oven in your house, you burn your stove in your house, right? All these things produce carbon dioxide, water vapor, and heat. It's when we get the intermediate conversion from carbon dioxide to carbon monoxide that we have an issue. So what they did here is, if you've ever seen the movie Backdraft, right? The doors are closed, the fire's burning in the room, and as soon as you open up the room, the flame comes out and it's looking for air, right? Starving for air. What would happen is we blocked off an appliance, the flames would come out the front looking for oxygen, looking for something to breathe. The flame is a living, breathing thing, right? And it needs air. So as the flame rolled out the front of the boiler or the furnace, it would catch the wiring on fire, burn up everything, and that was not such a good idea. So people were getting killed by fires back then. If you go back and look at a lot of why appliances were built the way they were built and why we have an electrical code, it's because fires. Everything was catching on fire back in the day, right? I mean, it was pretty darn common. So if we separated the appliance from the draft, if this became blocked, right, if the chimney became blocked, then the flue gas could come out and just spill into the space, and the carbon dioxide, water vapor, and heat was a lot safer than a fire. Because the odds are that as long as the boiler is burning correctly, you just realize you had high humidity in your house. A lot of people don't realize if you walk in a home and they complain about high humidity all the time, you better start looking at the large appliances for dumping flue gases into the home. So the draft diverter, the whole idea of it here, and let's see if this, oops, I can't work Joe's at the same time as mine, is that when the fire burns, it creates a natural draft. So when the fire goes up there, the warm air rises, and as it rises, it goes up, and it just goes up into the area of low pressure, right? Pressure always flows from high to low. So if you were to actually take and measure right here, and you were to measure your draft here, it would actually be a positive pressure. There's actually positive pressure in that part of the breaching right there. There's negative pressure here where it's tied to the chimney, positive pressure right here. The positive pressure is going to flow up in this area, and because there's a negative pressure here, it's just going to pull those flue gases in along with dilution air up that hood, right? So when we have our air come in, there's all the secondary air that comes in, and these are actually, once you start testing older appliances, you think, oh, these are going to be really, really inefficient. And you look at the excess air readings, you can see they're actually running really, really low excess air, and the excess air is very, very well controlled because these appliances took air in at exactly the same rate that they went out. It's just natural draft drawing that up in there. Now what happens when we get a bird in the chimney on there, right? We get spillage, and if everything is working correctly, we get carbon dioxide, water vapor, and heat. That's not going to kill anybody, but it's a pollutant. We don't want to have that in our home in there. But when we have carbon dioxide, water vapor, heat, and CO, and that's when we have a problem, right? And so that's what we're trying to avoid at all costs in there. Draft has got to be established within the first 5 minutes of starting the appliance. You've got to make sure that it's running. It could spill for a few minutes when the chimney's cold, especially like the first part of the year. You go out and it's been a no heat and it's been uncomfortable for hours and hours and hours. You could get a little bit of spillage, especially if you're talking a concrete or masonry chimney. That's where you'll probably see that. On metal, it's going to warm up right away and you'll establish draft very quickly. But on concrete chimneys, which we have a lot of up north, it could take up to 5 minutes. You want to check across the entire length of that am I picking up another mic here? It just seems like it went up loud all of a sudden. All right, you want to go across the entire length of the draft hood here and check for spillage. This is a little wind indicator here. It's just producing a little bit of smoke. We're going to go across the entire front of this, and we're going to check for spillage on there to make sure that we're not spilling flue gas. When you see these get rust up on top here, it's not because the manufacturer's made bad metal. It's because it's getting flue gases that are spilling, and they're causing that, there's acids and flue gases, and those acids are eating that metal up there. So that, whenever you see rust or anything up on the top here, that's an indication you have spillage. That's an indication you have a system that has a very serious problem you need to look into. You don't want that flue gas spilling in there. So look for evidence of rusting, staining, and evidence of spillage. Draft on a hot water tank. Again, must be established within 5 minutes of starting. So many guys walk in, they test the furnace. I have seen more hot water tanks making large amounts of CO than I ever have furnaces. Hot water tanks are a huge potential source of CO. Anybody know why? Who puts in hot water tanks? Homeowners do, yeah, and that's the problem, right? Because they don't have tin snips to cut their flue pipe down. They just shove it all the way to the back of the chimney, and it's hitting the back of the chimney, and it's not venting anywhere but in the house. You'll see issues where they don't use a backup wrench. They torque on the gas valve. Now the burner's sitting sideways in there. You'll see rust that piles up inside there because their kids constantly taking, they have 2 daughters at home and they're running the hot water down empty all the time, and it's rusting and dripping inside there. So hot water tanks should always be tested, again, all the way around the draft hood to make sure that we don't have spillage on there. We're going to look for evidence of rusting, staining, same thing, melted plastic plugs in a water line. So a lot of what we do in combustion analysis is not just about the combustion analyzer, but using your eyes and using a little common sense. If you don't start noticing these things and you start talking yourself out of looking at them, you're going to miss some serious problems. This is probably one of the most common ones I see out there today because we're common venting appliances. And I used to, when I was teaching classes, I taught at Cuyahoga Valley Career Center for 12 years. And what I did is I had a metal Vestas chimney on top of it. I put a big draft inducer motor, a power venter on the top of it to put a rheostat on it. So I'd start the furnace up with the kids. I'd have the draft going on there just like normal. And then what I do is just decrease the draft. Walk over there, say test draft. And I'd have them check the furnace, and they go through and they test everything, and they say, yep, it's all working good. And then I'd say, are you done? They say, yeah. And I said, good, you just killed your customer. And they look at me like, what? What the heck are you talking about? I'm like, come over here. We walk over to the hot water tank, and all the flue gases for the hot water are spilling out from the furnace, are spilling out the hot water tank because there was no place for it to go in the chimney. This is very common when people undersize chimney liners or undersize chimneys, that as you start that furnace up and it's running, it has draft initially, but as the flue gases fill up the chimney, it starts to back up in there and the draft starts to decrease to the point where we get spillage in the chimney. Chimney liners, right? Chimney liners collapse. I think I got a slide. It's not on this one. The chimney liners collapse, chimney liners fail, chimney liners aren't put in correctly, guys don't pay attention. And this, whenever you see a common vented appliance, you need to make sure that when this appliance is running that you don't have, there's a chimney liner right there in the bottom corner of it. So that is a very common problem. When you walk in, a lot of you guys don't realize part of the International Fuel and Gas Code and part of the National Fuel and Gas Code is actually inspecting the chimney when you go out there and you do a service on there. So you're supposed to actually take the chimney apart, take the stack off, take a look inside there. This one was absolutely full of aluminum beads, top to bottom. Because what happened was this is a masonry chimney liner. The masonry is cold. They didn't put a sleeve on there to protect it from condensating. The condensate collected on the inside of the liner, and again, it's an acid in there that acidate the aluminum, and then you end up with a rotted out liner sitting there, right? So these are common problems that we see out in the field all the time. But this one here is one that's near and dear to my heart because I've seen this happen more times than one. Well, the Y, you can have the Y on there, that helps divert the flue gases in the right direction, but if it builds up and it backs up is the problem. It doesn't matter where a Y is the correct way of doing it. So normally we'd have like a 3, 4, 5 or a 4, 5, 6, and you'd Y it in. But the problem is when it goes up, if the pressure builds up, it's static pressure, right? It just builds up a pressure in there, and it's just got to have somewhere to exhaust itself so it exhausts out the hot water tank. And that's the most common problem when you see those things melted out there. All right, so now we just went through a whole bunch of visual inspections. We made sure we got draft. We made sure the flue gases are going up the stack. And let's talk a little bit about setting manifold pressure. All right. First thing we got to understand is that every single appliance is engineered. A lot of guys they get crazy when you start talking about working on a gas appliance. And we talk about setting gas pressure, and we talk about changing orifices on the gas appliances or whatever. This is the business that we're in. We're in the HVAC business. In fact, anybody here do work on propane? Bunch of you guys, right? You guys don't really panic over changing orifices, do you? Right? You have to go out and convert natural gas appliances to propane all the time. For guys that are in classic gas markets that never convert appliances out there, maybe you guys have seen for years, it's 3.5 inches. Got to set it at 3.5 inches. What does that say right there? Manifold pressure. 3.0 to 3.8 inches. That's on a 90 plus furnace at my daughter's house, right? It's an ICP product, carrier product. Now it's saying that there's a range of adjustable pressure. It's not just 3.5 inches, it's a range of pressures on there. And you'll see this more and more as people are making sure that you get the input correct on furnaces. So here, I'm just setting up the fuel pressure on the furnace. And now we get the fuel pressure set, now we want to clock the meter. This is a step that almost nobody does. If you look in every single furnace manufacturer's manual, there's a section on clocking the meter. This, in my opinion, is the most important step on making sure we're getting the appliance set up right. If you think about it, there's not too much we can adjust on a natural gas appliance. In fact, there's only two things. What are the two things we can adjust on a natural gas appliance? Input, gas pressure is one, and what's the other one? Airflow. Blower speed. That's it, right? Guess which two things don't get set correctly in most appliances? Gas pressure and airflow, right? That's the stuff everybody forgets about. And clocking the meter is a step that we learn about in school, and we think it's like some kind of theory that we should clock the meter, but nobody does it. And the meter is this is one of the most important steps. Now here's why. And here's why you don't ever adjust a furnace with a combustion analyzer. A lot of guys say, I'll just put it in there, I'm just going to adjust the gas pressure until I get 50% excess air. You'll hear that in the industry. You don't want to do that. This is called a Loeb index. And what that is a measure of the interchangeability of fuel gases. But what it's showing us here is that there is different heat content. So anywhere from 1035, 1030, 989, 1041, 1019, 1035. Heat content varies of natural gas across the country. In Florida, they have a lower heat content of gas than we do up in Ohio. And a lot of times what the manufacturers do is they actually add in other gases like propane to get the heat content where they want it. They'll trim the gas on there. Problem with this is the heat content, if you were to actually have a calorimeter, and again, CSA Labs went down there years ago, the heat content varies not only hour by hour, but almost minute by minute. The heat content is going up and down of the gas. And so the big problem is if we don't set it up for average heat input, we don't know whether the heat content is high or the heat content is low when we're adjusting that appliance. You need to make sure that you're setting it up clocked and get your average heat content for your area. Set your appliance up for the average heat content because that 50% excess air is designed to make sure we always have enough air if the heat content of the gas increases. Right? So as the heat content of the air goes up, we need more oxygen. That excess air is making sure that we don't make carbon monoxide, and we want to make sure we get that input correct on there. So what we've got here is I'm clocking a meter, and one thing you can tell me, what can you tell me about a gas meter? There's something really important about gas meters that can assure us that they're accurate. It's the same thing when you go to the butcher and you look at a scale, or you go to the gas station and you look at the meter. What can you tell me about there? There's always a what on there? Some kind of a sticker. Certification, yeah. These are utility grade meters, okay? Now they're very accurate. They're also temperature compensated. A lot of them are temperature compensated now to 68 degrees, meaning that it's always going to give you a precise reading of the input of natural gas. So here I'm just clocking a meter on there, and then there's a scale here that simply tells you when you clock the meter here how many seconds it took for the meter to clock and then what your input is. Now there's different dial sizes, a half, a 1 foot, and a 2 foot, but the key thing here is that table assumes 1,000 BTUs per cubic foot. So whenever you clock the meter, whenever you look at the manufacturer's thing, they're going to tell you that there's an assumption made for the heat content of the gas, and you actually have to mathematically correct that. And the way that you correct it, and we'll talk about that in just a minute on the next slide here, but here I clocked it at 48 seconds there, and at this point here, we got to determine is the input correct? Do we have to change the fuel pressure? Do we have to adjust the orifices, change the orifices? What do we have to do? Right? So in this case here at 48 seconds, I'm at 75,000 BTUs of input, and I might have to correct that for my heat content. So let's talk about that. If your supplier's giving you 1,025 BTUs per cubic foot and your chart's at 1,000, all you do is just 1,025 divided by 1,000, multiply it times 1.025. So if you had 86,000 on your chart times 1.025, it'd be 88,150, right? It's just a correction for the heat content of the natural gas. And it could be a multiplier that makes it higher or makes it lower depending on what your supplier heat content is on that chart. This is really slick, and I found this. If you ever want to learn a lot about our industry, you got to learn it from the dead. Dan Houlihan would say is the dead men that came before us, right? Things have gotten so commonplace in our textbooks today. You know, you go out and you buy a copy of refrigeration air conditioning technology. You won't find this formula anywhere in there that it tells you that if we know our current input and our current pressure, we can calculate what our new manifold pressure should be based on our desired input. It's a formula that comes out of a book from 1920 when it was called Installing Gas Burners in Coal Boilers, right? So it was all about setting up coal on there. Now, these formulas are things that are lost because we, as an industry, we don't talk about gas burner design and retrofitting appliances anymore. And this is what we use in measureQuick, this exact formula to calculate out what the pressure should be. So if we had 90,000 BTUs equals 88,150 divided by P2 divided by 3.5, I can calculate out if I want to have 90,000 BTUs output, what my P2 should be is 3.65 inches of water column. So we can set it at 6.5. It just allows us to correct for the gas pressure on there. So when they're saying 3.0 to 3.8, that's what this is all about, is getting correct input on the appliance, right? Now measureQuick, what we do is we simply clock the meter. You'll notice that there's a couple of different things here that are pretty important here. Number one is we have the heat content of gas. And pretty quickly we're going to use your geolocation on there to pull this heat content in off that EIA website you guys just saw. So you won't have to set this, it'll just do it automatically for you. And here's just 3 examples here. So we clocked it at 38 seconds. It tells you that because it's 2.74 inches of water column is the target, it tells you that we need to downsize that orifice and reclock the meter, because at 2.74 we're below 3 inches of water column, so that's too low, so we need to downsize the orifice. In this case here, the target's 4 inches of water column, so we need to increase the orifice size. In this case here, it falls in the range, so now all we gotta do is just set it at 3.68 inches. So it'll tell you all those things. It runs all the calculations in the background, so you don't have to do it by hand. On a propane system, there's a couple different things you can do. One is get a sublet meter for propane and install it in line. And that might be and it's a one-time thing when you're doing a propane installation. You just what I did is take 2 flexible gas lines, connect the propane meter in line, literally clock it in the basement, which is sort of nice. Get the input correct on the appliance. Propane it's a son of a gun too, because you get a lot of different heat content from different propane manufacturers. So you got to call them, ask them what the heat content of their gas is, and then the appliance is engineered for natural gas. It's retrofitted for propane. So sometimes you're not going to get the performance out of that appliance on propane that you would on a natural gas installation. And it's just the way the appliances are built. But input on propane is absolutely critical, because if you don't get the input correct, you're going to have issues with carbon monoxide, with sooting. It can be a nightmare. There's probably more. If you see a furnace that's sooted or have bad installation, it's typically a propane installation more than natural gas, because somebody didn't do something in the conversion correctly, right? So a sublet meter you can buy. You can go on Amazon and buy a sublet meter, and that's the easiest way to test that. So on a 90 plus furnace, and it depends on the efficiency of your furnace. If you have an 80 plus furnace, not a big deal. If you have a 90 plus furnace, it's a huge deal, because the difference in getting the input correct, the only way you can adjust the amount of air going into that appliance, because there's no shutters or anything else. The only way you can judge the change the amount of air is by getting the input correct. So whenever you have an orifice, a gas orifice, and you fire gas through it, it'll actually entrain air in the proportional velocity of the gas. So as the gas pressure goes up or down, it's going to get exactly the same amount of fuel gas mixture in the primary air all the time. That's why we can run a furnace down to 1.7 inches on low fire and up to 3.5 on high fire, because the Bernoulli effect is just going to train the right amount of air in. Well, what we can't control is the amount of secondary air. And secondary air is the air that goes in around the flame. So what happens is we're either going to pull in air or we're going to pull in gas, right? Gas and heat. So when the flame is too small, we have a high amount of secondary air going in because there's just no gas to displace it, no fuel to displace it. And what happens is it dries out the flue gases. So in my case, in my house, I had input incorrect. I had a 94% full modulation ream furnace. Put the combustion analyzer in, it's running 90% efficient. Like, why the heck's this thing running so low? Why isn't it running closer? And I pull off my condensate drain, I have no condensate running out of that drain. Well, I have 75, 80% excess air. Huge amount of excess air. That excess air dries out the flue gases, right? Now you go, well, it's only 4%. Well, if my gas bill, you know, over the course of a year, let's say up in Ohio, I might spend, you know, maybe just shy of $1,000 a year on gas. 4% of that, right, 40 bucks a year, over a 20-year period is substantial. So getting that input correct right the first time is going to save you anywhere from 4 to 7% on your gas long term. And you're going to get the appliance running the way it's designed to run. I mean, that's the other thing is if you don't make condensate, a lot of times what you'll do is you'll pull flue gases backwards up the secondary heat exchanger. There's a trap in there, and that trap has got to have water in it. And if it doesn't have water, the induced draft motor is going to pull, because it's on the collector box, pull backwards up, and then we have some serious problems on there. So you want to make sure if it's a condensing appliance, it's actually condensing. You'd see high excess air, yeah, or high oxygen. I typically, when I'm looking at an appliance, a lot of guys watch CO2, they're older oil guys. I watch excess air. Excess air, you know, I want to have it anywhere from about 35% to 50% excess air when it's set up properly. On a first stage on an appliance, like if you're talking about a two-stage appliance, you could easily have 100 to 150% excess air because we can't control the secondary air. Right? Now here's the other thing that a lot of guys don't understand. Two-stage appliances do not save you any money at all. Right? They don't save you any money. In fact, your appliance runs worse on the low stage. It'll run around the 90% efficient range versus 97%, let's say, on the high fire. The only reason we have modulation and we have two-stage appliances is for comfort. That's it. It provides us comfort. So you're getting more comfort, you're sacrificing efficiency, okay? So like my full modulation furnace, it runs at 90% a good part of the year. Right, the only time it comes up in the high fires when early in the morning when it's when I have the house set back, it warms up, fills the trap up, keeps so I don't pull water up the secondary heat exchanger. But most of the time it's running in this low fire. But it's like having a gravity furnace in my house. Right, I knew it wasn't as efficient, but I wanted the comfort of having it out there. When we're setting up an appliance here, what we're trying to set it up for is the highest efficiency with a certain amount of safety here. So what we're always going to set up the appliance so we're in this zone here. This is what we call stoichiometric combustion. This is when you have, when you have just the right amount of fuel and just the right amount of air. So if you look at the bottom here, there's no excess oxygen, there's no excess fuel, there's no excess air, right? That's stoichiometric combustion. We want to be in here where we have some excess air. Now here's the thing you got to remember, is even though you have excess air, you can still have carbon monoxide. I keep bumping that crazy thing. You can still have carbon monoxide on there. So just because we have excess air doesn't mean we don't have CO on there. And so what we want to set the appliance up for is this range here, which is typically, and again, at 30 to 50% excess air range on the appliance. So this is what we see when we're graphing. This is actually off of a testo analyzer. You can do the same thing off of off the AccuTools analyzer. This is a graph of combustion analysis. This is typically what we want to see. So we start the appliance up. If you look here, this is efficiency. This is oxygen. The green is CO undiluted, and this is stack temp. So if you just start with the O2 here, right? We start at 21% oxygen. We start the appliance up, and we see this dip right here. Why do you think we see this dip right here? What happens when we first start an appliance up? And warm up, and we also have a lot of gas, right? We're feeding a lot of gas in because the igniter's starting to glow. Igniter's glowing, they open the gas valve up, and there's going to be a little bit of gas that goes through, and it's sort of woof, right? When it lights off, it's got a lot more fuel than it needs initially, so we see this dip in oxygen right here, right? We see this dip in oxygen. Notice we also have CO right here because we have excess gas, and we have we're pulling the O2 down. But almost immediately that O2 starts to rise up. This is only minutes here, so this is a minute after it lit. Within a minute and a half here, the O2 is starting to stabilize, the CO air-free drop down to 0, right? The stack temperature slowly rising. Why does the stack temperature, here's one that people say, well, steady state efficiency of a furnace is when the stack temperature stops rising. The stack temperature will never stop rising. Why not? Return air is rising, yeah. As the return air rises, the stack temperature is going to rise. And then here's our efficiency. So it started off here higher, and you notice the efficiency is also dropping off. Why would our efficiency drop off? Because our return air is going up, right? Heat either goes two places, in the house or out the stack. So again, as it runs, you're going to have a small drop in efficiency, but overall it's running right in that 80% efficient range. Now contrast that to this. This is an appliance under duress. This is actual appliance I went out on. This was at a Lorraine Metropolitan Housing Authority. O2 on the bottom right there, you'll see that the O2, when this is not when the appliance is starting, it's just running. O2 is all over the place, right? And you can see there as that appliance is running, the CO is down at 0 parts per million. But then all of a sudden when O2 hit in the 8% range, the CO went through the roof, right? Straight up. This is a characteristic most guys don't understand with gas appliances. CO is like a hockey stick. You have air and fuel going in, everything looks good. You keep trimming down the O2, and everything looks good. You can be right at 0 parts per million, but you literally cross 0.5% of oxygen and it'll go from no CO to CO through the roof. Notice that where that's at, that CO undiluted of over 3,000 parts per million. Now I pulled my stack out at that point because I was watching this thing run and I saw my analyzers are going to get pegged. So I pulled the probe out of the stack. That's why my O2 went back up to 21% right here. And then put it in here. Anybody have an idea what could cause stuff like this? And this is where, again, I went out, this is a Lorraine Metropolitan Housing Authority. This is a Viessmann boiler, sealed combustion, bringing in air from outside, probably a million BTU boiler, right? Big boiler. This is a weird case of events out here. What could cause something like that, right? Everybody's out there, there's a pile of pressure switches on the floor, right? Because it's got to be a bad pressure switch, right? This is actually from an elevator. Right? What was happening is every time the elevator would go up or go down, it was creating a plunger effect on the building because they had gone and taped off part of the elevator shaft that was the ventilation for the shaft. So when the elevator would go up, it would depressurize the room when the elevator would go down. And what you're looking at is the elevator going up and down a couple stories versus the elevator going to the 6th floor. The reason we saw this is because we were graphing it on a combustion analyzer and we're going, what in the heck is going on? And I'm listening and hearing the elevator going up and down, and sure as heck, that's what was depressurizing the space. Now here's what I want you to understand. This is a sealed combustion appliance. Sealed combustion. So it's exhausting outside, bringing air from outside. This was overcoming, this pressure was overcoming the sealed combustion of that appliance. This is actually, when we tested it, because the other thing they did was they abandoned the chimney in the building, abandoned the chimney altogether. This is probably a 10-story building, huge chimney. The pressure in the chimney was negative 50 pascals. So we had an open boiler space with an open chimney in there, sucking the air out. We have this plunger effect of the elevator shaft going up and down. We have all these perfect series of events that are causing all these problems here. And you can see this is definitely combustion under duress. If you weren't testing this with a combustion analyzer, you'd never see this stuff happening. measureQuick we just incorporated into gas heating, and here's the big reason why. When I first bought a combustion analyzer, it had all these readings on it, and I had no idea what all those readings meant or what they were for, right? Because we have stack temperature, we have O2, CO2, we have excess air readings, we have efficiency readings, we have CO air free readings, we have, you name it, there's probably about a dozen readings that the analyzer will make on there. One of the things we did with measureQuick was we tried to tie targets to all these so you can actually see if they're in the safe zones, if they're in a high efficiency, low efficiency, if the input's in the correct range or not. Very, very visual, and we've built that all into the product, and that's all working. Well, there's a set of tools we recommend with that, and what we're trying to do now is instead of looking at the appliance measurement by measurement, we're looking at the entire appliance at once. Furnaces are dynamic, and here's the problem. If you're not looking at everything at once, if you're not watching things, you miss things, right? Because again, we're talking about that gas appliance. It's hooked to a distribution system to get the air out where it's got to go. It's got a ventilation system. It's got a gas supply system, right? There's things that happen. You know, you're standing down there, if you're not watching your incoming gas pressure, how many of you guys have seen furnaces lock out on intermittent flame failure, right? You go out there and you clean the igniter and you do all kinds of other things. How many of you guys have constantly measured your incoming gas pressure and noticed times when the gas pressure dropped too low for the regulator to regulate, and now we got a flame that is not working correctly? Somebody turns on gas logs, somebody turns on the dryer, somebody turns on something else. If you're not watching incoming gas pressure at the same time you're watching your manifold pressure, you're missing a problem that could be potentially happening. If you're not watching your temperature split at the same time, you're missing things that could be happening. If you're not watching your combustion, you're missing things that could be happening. That's why with all the Bluetooth tools that are out there, we recommend, you know, in this case here, I got 4 manometers hooked up. People think sometimes I'm crazy, but this is what differentiates a technician that catches problems versus somebody that misses them consistently and walks away. This is about, you know, it's a small investment in tools. If you think about where we've come as an industry, it's like the best time ever as an industry, because the cost per point of measurement has just dropped down next to nothing, right? The cost of a manometer, they're not expensive anymore, but now you can see these things in real time as they're happening, right? So here's a couple things we want to do with measureQuick. We got to profile the system. Profiling is the most important part when you're doing combustion analysis. And by the way, you don't have to have a single digital tool to use measureQuick for combustion analysis or any other thing, all right? Because one of the things I did is I built it so that you can, there's input boxes here, so you can tap on these boxes, input your temperatures, input your pressures, right? So if you don't have 4 manometers, you can input stuff by hand and still use all the diagnostics and everything else measureQuick does. But the key things here are we want to profile the system. Profiling the system is telling me what type of a system, I guess you just can't see that one. Profiling a system is telling me what kind of a system it is. Is it a 90 plus? Is it an 80 plus? I need to know what to expect. Obviously, the stack temperature on a 90 is much different than the stack temperature on an 80, right? After we profile it, we're going to make sure our temperatures are in the right range. So this is supply air, return air temperatures. Can return air temperature be too cold to actually set up the appliance correctly? Absolutely, right? Yeah, absolutely. It can also be too high. What about an 80-degree day in Florida? Would you want to run the furnace? No, it doesn't work, right? It's not engineered for that. So there's every single reading we make has a target. This is probably one of the things I'm most passionate about in our entire industry, is you should never ever make a measurement unless you know what you should expect, right? Honestly, if you're making a measurement and you don't know what to expect, why are you making it? Are you making it just to put a check in a check sheet to say, oh, here's the gas pressure was, or here's what the CO was, right? And how many guys have you guys seen sitting in their truck on Tuesday when they got to come in the office filling out their paperwork, right? And they're writing down 118-pound suction, 350-pound high side, 9.2 degrees of superheat, 10.7 degrees of subcooling, right? How do they know all this stuff? Because they've memorized it from all the jobs? No, they know those are the readings their boss isn't going to question, right? So if they just write those readings in, they'll be good to go. Don't tell me it doesn't happen. I mean, I've seen it over and over again, right? And so they get tired of tech support guys. This is I talked to the guys at Carrier, Train, Lennox, Goodman. They get guys on the phone. What's your superheat? Oh, it's 10 degrees. What's your suction pressure? What's your suction line temperature? Okay, that's not 10 degrees of superheat, right? You need to know what your measurement should be, and this is what a big part of what we're doing in measureQuick. We're making sure the temperatures are right, the pressures are right, the input's right on that appliance. We're making sure it's breathing okay. Does it have enough oxygen? Is that input correct on there? And then if you have a question, what's up here, right? And what we got here is just a target that's out of range. If you tap on any one of these targets, it'll tell you what that reading is. It'll tell you about it, and a lot of times it'll tell you what to do about it. So now you know step by step what to do. So everything on there is calculated out, so you can do that. All right, combustion testing, gas furnace. Very important on here when you're testing multiple cell appliances, like an old 70% efficient furnace on here. You're going to have to do 3 combustion tests. Every single cell is its own little combustion chamber. They're not tied together. Again, what's the job of the draft hood is to separate the appliance from the draft. So you're going to test each cell in the undiluted flue gas. Undiluted flue gas is an important term. We never want to test flue gas once it's gone through the dilution air hood or draft hood on there, because that flue gas is highly diluted. We want to test it when it's coming out of the combustion chamber itself. Verify the base pan seal. This is again that CO poisoning Bill and I ran across years ago. 90 plus furnace. They actually condemned it. It was a comfort maker furnace, cracked heat exchanger, reasonable standard of care. The guy shut the appliance off, said, "Lady, you got a cracked furnace. Let me get a new furnace out here and we'll get it put in." Take the old furnace out, put the new furnace in. They reused the existing venting system, right? 3-inch exhaust vent going out. Went from a single stage appliance to a 2-stage appliance. Well, Lennox furnaces on these required an exhaust accelerator, so they didn't put the exhaust accelerator on. And so now they got a furnace that's making carbon monoxide, and it's exhausting it outside, which was all good, except it's exhausting it underneath an overhang for a gas fireplace that's got a ventilated soffit. Because it didn't have the velocity to carry it out from the house, it pulled it back inside in the home through the ventilated soffit. Well, how did it do that? Base pan on the furnace, on the bottom. A lot of these furnaces come with either a removable base pan if you're going to use it with a bottom return, or none at all, and you got to pan your own return under there. That base pan was loose, depressurizing the basement. So now I got a negative pressure in my basement. I've got carbon monoxide, and I've got a path for that carbon monoxide to get back in the house, and that's exactly what happened on there, right? These things are a perfect chain of events, so you got to look at the entire appliance and make sure that we're doing it right. Excess air, 31 to 91%. On this type of appliance, O2 reading 5 to 10%. You know, each one of these, and these are all laid out in the combustion guide on there, sort of step by step how to do that. So I'll flip through these and we'll get through this quickly so Brian doesn't yell at me. Understanding combustion efficiency versus AFUE. This is probably one of the most important things. You guys are going to buy a combustion analyzer. You're going to go out there, you're going to stick it in the stack of this old piece of junk appliance. And you're going to go, oh, this is burning pretty good. It's almost 80% efficient. And it is burning pretty good. But what you're not considering is all the standby losses of that piece of equipment. A combustion analyzer measures combustion efficiency, not appliance efficiency. So here I've got a draft hood. That draft hood loses 10% of my efficiency of my appliance because it's constantly sucking air out of my home, whether I'm burning it or not. Standing pilot loses 10%. Uninsulated cabinet losses. So yeah, I got 81% combustion efficiency, minus the draft hood, minus the standing pilot, minus the uninsulated cabinet. That's a little bit more representative of the AFUE than appliance. So consider when you're looking at an appliance and you look at that combustion efficiency, that only tells part of the story, right? How do we think about the evolution of furnaces as we go. When we went to an 80% efficient, we eliminated the draft hood first. Did you guys remember we had 80 pluses with standing pilots? Any of you guys remember those? Right? Then we eliminated the standing pilot. Right? We got rid of the standing pilot. Then we saved more gas by putting in a secondary heat exchanger in it and getting the secondary heat exchanger. So a 97% AFUE replacement actually does increase a 41% efficiency. So that could drop that $1,600 gas bill down to $656. All right, the rest of this is just going over different spots on combustion tests on here. This is all in the guide. You can download that. A couple other things on differential temperature testing. Second most important thing on appliance, you want to be in the center of the range on there. You don't want to be either end of the high end and the low end, because we can either cause condensing in a non-condensing appliance, or we don't leave any room for the filter to load up with dirt. Right? So again, combustion analyzer can be used for that, to measure the differential temperature with a couple of nice field piece K-type thermometers. All right, boilers, again, make sure you're testing in the undiluted flue gas below the draft hood on there. And then we're going to test the rise of the water on a non-condensing appliance. We don't want to see that water coming back at less than 140, or we're going to get condensation in there. Oh, the old book? I'd have to look it up. I honestly don't remember what the name of the book is. It's a series of small books that it's called Installing Gas Burners Underneath Coal Boilers, I think it's the title of it. But I'll look it up. I'll look it up. I'll put something online on it. Yeah, so what they do is they have a 3-inch flue pipe. They neck it down to 2 inches, and it's just for a short range of span. So think about, it's a lot like evacuation. When you're doing evacuation, the larger diameter tube causes a decrease in friction. So if we just neck down the exhaust just at the end of it there, it doesn't cause a lot of friction where the pipe becomes a problem. It just accelerates the exhaust, speeds it up, increases the velocity, and throws it away from the house. So that's common on Rheem does that. Lennox does that. You'll see a lot of 90 plus appliances where you got a 3-inch and then it necks down to 2-inch when they exhaust it out of the home. It'll work with back racks if you got the QR code. It'll scan the QR code and bring the readings in off the back rack. So it'll work with, and you can also input the readings by hand in there. But yeah, everything we do in measureQuick is set up so you can input the data by hand if you need to. Combustion is combustion, so for the most part, we always try and get the right amount of fuel, the right amount of air in there. That's why we built all the targets in off all the different appliances. That's when you ask how important it is, that's the profile. So we got to make sure we get the right profile put in so we know what we expect coming out. The biggest thing that changes is your oxygen reading and your stack temperature. Right, your stack temperature can be anywhere from 90 degrees up to 600 degrees. And it all depends on the appliance. And your O2 could be anywhere as low as, let's say, 30% all the way up to 150%, depending on the appliance. So yeah, it does have a wide range of anticipated outcomes. You gonna shut me down now?
Yeah, no more questions.
All right.
This could go all day. This is just like the podcast, where I can't get a word in edgewise.
There's good reason for that.
Everybody, Jim Bergmann.
Thank you much.
Thanks for watching. Make sure to follow measureQuick and AccuTools on social media to find out more with what they have going on. Really nice tools and really great software. So go check them out on YouTube, Facebook, Instagram. They've got accounts all those places, and stay up with all the latest with measureQuick and AccuTools. Thanks for watching.